Hello, everyone. The topic of this presentation is Burgulence modeling using a machine learning assisted mimetic framework. This is part of research work that was conducted as joint effort between UC Irvine and San Diego State University, funded by the Computational Science Research Center. It's well recognized that modeling the subgrid scale stress tensor term for the closure of the Burger's equation for modeling turbulent flows is quite often a challenge. If we consider the partial differential equation that's used to model turbulent flows, we use the Navier-Stokes equations as the basis. And it's well known that the Navier-Stokes equations and the partial differential equations contain nonlinear convective terms. And these nonlinear convective terms are often quite difficult to model from a spatial discretization standpoint. And they're difficult to model in the sense that they can lead to aliasing errors if they're not modeled properly. And that's the reason for requiring special attention when it comes to spatial discretization. The mimetic methods that are considered in the present work are the result of the Castillo-Groen and the Corbino-Castillo mimetic operators. And these mimetic methods, they possess a discrete equivalent of a global conservation law and has therefore been proven to leading to more accurate spatial discretizations. The objective of the current work is to establish a machine learning-based mimetic framework in order to help uncover the subgrid scale stress tensor terms for modeling the turbulence of the viscous Burgers equation. The aim here is to use the mimetic method to obtain the ground truth, otherwise referred to as the direct numerical solution, using a fourth order mimetic scheme. Once we obtain the DNS ground truth data, we use that data and then filter out the data using filtering techniques and then feed that data to a neural network and be able to use neural networks to be able to model the subgrid scale stress tensor closure terms. And we compare the resulting neural network model, the neural network machine learning based model, with other filtered techniques such as the Smagorinsky model and validate the model accordingly. The equation that we consider here is the one-dimensional Burgers equation that's shown in equation 1. The term in parentheses here refers to the convective term, which is a nonlinear term. The term on the right-hand side is the Laplacian operator, which refers to the viscous dissipation that's available within the Burgers equation. If we filter out the Burgers equation, we end up with a term that's shown in equation 2, where the top hat for the velocities you refer to the filtered velocities. When we filter out the Burgers equation, we pick up a subgrid scale stress tensor term tau, which is shown by equation 3. And it is this filtered subgrid scale stress tensor term that needs to be modeled as part of the turbulence modeling. We discretize the above equations using the mimetic discretization scheme. Once again, the divergence and the gradients that are mentioned here are obtained from the Castillo-Groen and the Corbino-Castillo mimetic methods. The ones that are implemented in the current work use the Corbino-Castillo operators, where D is the divergence operator, G is the gradient operator, and L is the Laplacian. The mimetic operators satisfy the terms that are shown in equation 5, where we're able to obtain high-order discretizations for the divergence, the gradient operators that are even orders of accuracy and even orders of accuracy at both the interiors and the boundaries of the grid, and thereby leading to more accurate discretizations. What is shown here on this slide is the energy spectrum as a function of wave number. The Kolmogorov turbulence hypothesis states that at low wave numbers, energy is preserved, and at high wave numbers, as the wave number increases, the energy dissipation range comes in. And numerically speaking, it's quite difficult to preserve this energy dissipation at high wave numbers. What we see here is the green line where the Burgers equation has been solved without including a turbulence model for the subgrid scale stress tensor term. And we notice that there is a pileup or an energy buildup, which shows at high wave numbers, which is non-physical from a Burger's equation, Burgulence standpoint. On the other hand, the black line here represents the machine learning based model, which adequately dissipates energy at higher wave numbers. And this is also compared with the dynamic Smagorinsky model and the filtered direct numerical simulation model, where in all cases, the energy dissipation is adequately preserved at higher wave numbers. Further efforts are currently underway to quantify this in higher dimensions and also quantifying this not just for the Burger's equation, but also for implementing the machine learning based mimetic framework for the Navier-Stokes equation. Thank you for your attention.